now we're going to talk about a few different characteristics of derivatives and how they relate to graphs, both of original functions and second derivatives. And sort of the last of our hodgepodge of things about derivatives before we start to put those together in more concrete ways with some more actual examples of working with things in a bit more real-life situations. But before we get into that, a couple of little tidbits. First thing I'm going to mention is the first derivative test for finding extreme points. And so by extrema, of course, I'm referring to extreme values of functions. Absolute maximum, absolute minimum, local max, local min, that sort of thing. I'm going to dive right into an example working with this. This is example 1 off of page 210. And we're asked to find local extrema for f of x equals x cubed minus 12x minus 5. Now, it's a polynomial, so that makes our life a little bit easier in that we're not going to find any place where the derivative doesn't exist, and we're not given any hard endpoints to this. So all we really care about, in this case, is places where our derivative is equal to 0. So we find our derivative. It's equal to 3x squared minus 12x. And that is going to equal 0 when 3x squared equals 12, when x squared equals 4, or when x equals plus or minus 2. So, our only critical points are at x equals plus minus 2. I would also normally look for any places where the derivative doesn't exist, but again, where this is a polynomial, this will be differentiable everywhere. The derivative will exist for every value of x. Now, I can even go so far as to figure out what those values are. At 2, my value of my function is 2 cubed minus 12 times 2 minus 5, which is 8. 8 minus 24 is negative 16, minus 5 is negative 21. And at negative 2, I have negative 2 cubed minus 12 times negative 2 minus 5, which is going to be negative 8 plus 24 is 16, minus 5 is 11. So my critical points are 2 and negative 21 and negative 2 and 11. Note that I haven't identified these as extreme values yet, either local or absolute, because I want to look at a little bit more of this. So your first derivative test. Now what I'm going to do is I'm going to kind of think of a number line, going way back, that I'm going to break up based on where these critical points are. Negative 2 and 2. Below negative 2. Let's say I try negative 3. The prime at negative 3 is going to be 3 times 9 is 27 minus 12 is 15. Between the two values, say it's 0, this equals negative 12 or negative. And above, I'm going to end up with positive 15 again. So space there. So since I'm looking at the derivative in these spaces, that's telling me about slope. My slope is positive as I come up to negative 2, negative between the two values, and positive above positive 2. So let's think about what that means for a specific point. If I have a positive slope leading up to a critical value, which then switches to a negative slope, then that point must be a local maximum. Likewise, if I've got a negative slope leading up to a point which then changes into a positive slope, then that must be a local minimum. So just seeing how the derivative acts on either side of your critical points can tell you whether you're dealing with a local maximum or a local minimum in your setup. So my local extremes, I have a local maximum at -2 and 11, and a local minimum at 2 and -21. As this is a cubic function, there are no absolute extrema. Because as the cubic goes off, as x becomes more and more positive, this value for the function will keep getting higher and higher and higher. Similarly, as x goes negative, this value of the function will get lower and lower and lower. So there's no absolute minimum value or absolute maximum value. That's how I can find my local maximum minimum values and tell whether they're maximum or minimum or not. I'm also going to take a look at the b part of this, because the function's a little bit more interesting. So we're looking for the same as a, but for g of x equals x squared minus 3 times e to the x. So my first derivative, as I go through a product rule, I say that because people tend to forget about that eventually, I end up with my first part times the derivative of the second, plus the second part times the derivative of the first. What that's going to leave me with for a derivative, if I simplify a little bit, is e to the x times x squared plus 2x minus 3. Water. Which factoring will let me bring out the zeros in that quite easily. It factors to x plus 3 times x minus 1. Therefore, critical values at x equals -3 and 1. Now, both x squared minus 3 and e to the x are differentiable functions, so when I multiply them together, I get a differentiable function, meaning that there's not going to be any place where my derivative doesn't exist. So again, I only need to worry about the zeros of that derivative. So I can figure out my critical points. When x equals -3, y is going to equal 6 times e to the -3, and I'm going to use my calculator to get a decimal approximation of that. I have -3 squared minus 3 times e to the -3. That's about 0.29. And at 1, I have 1 squared minus 3 is -2. -2 times e is about -5.437. And I can also look at how the derivative acts here. For x less than -3, g prime of x is going to be, well, let's think our way through this. e to the x is always positive. If my x value is less than negative 3, then this term will be negative, and this term will be negative, so I'd have a negative times a negative times a positive, or overall positive. For x between negative 3 and 1, this is going to be positive times negative. And for x greater than 1, I would end up with a positive times a positive times a positive, or positive. So it's the same sort of arrangement as I had up here, meaning that around negative 3, positive slope to negative slope would imply that's the local maximum. Negative slope to a positive slope would imply this is a local minimum. Now, are there extreme values? We can think a little bit about the end behaviors of this function to work this out. As x goes more and more positive, this is just going to take right off, and so will this. So there really is no upper limit on this function. It's just going to keep getting higher and higher and higher. So there's certainly no absolute maximum value. If I think about the other way, though, as x becomes more and more negative, I mean, this is acting like a quadratic, so it would just be a larger positive number. But e to the x is dropping off towards 0, and it's going to drop off to 0 a lot faster than that quadratic is going to do anything. So overall, this thing would have a horizontal asymptote at 0 on the left side. So that means, since if I go off forever that way, it's just going to get closer and closer to 0, this thing should have an absolute minimum value someplace. And the only real contender for that is here. So this is also an absolute minimum. Okay, now I'm going to move into talking a bit about the second derivative, which we haven't done a whole lot for talking about with graphs yet, but we will do that now. So where your first derivative tends to talk about slope, your second derivative is going to be involved with something we refer to as concavity. So let's talk a little bit about concavity and the second derivative. And the easiest way to talk about concavity is with a diagram, and we'll think our way back. Well, we'll do a couple of diagrams here. If I think about our old friend the parabola, I would say that this shape is concave up, meaning the sort of caved in portion of it is pointing in an upward direction. So this I would say is concave up. And this, likewise, I would say is concave down. And you can certainly have both of these things occur within the same graphed shape. If I think of even a cubic, for instance, I have a region here where I'd say the graph is concave down, but a region here where I'd say the graph is concave up. And this point here, where it seems to switch from a downward concavity to an upward concavity, is what we would call a point of inflection. I apologize for that X being an awkward spot there. Okay, so a few written out statements on this. The second derivative of a function tells you the concavity of the function at that point. Largely with the sign. The same way that if the first derivative of a function is positive, it means the slope is positive and the function is increasing. If the second derivative of a function is positive, then the function is concave up at that point. Likewise, if it's negative, then the function's concave down at that point. And if your second derivative equals 0, then you are at an inflection point. Of f of x. Now, for anyone who's watching the news lately, we're talking about the virus and when things start to change in the shape of the graph for the virus, so you start to move from an increasing point to a decreasing point and that sort of thing. Some commentators will refer to the graph reaching an inflection point when it turns around, which is not really a correct use of the term. They'd be better off saying the graph's reached a maximum point or a minimum point, because an inflection point would just be a point like this, where your concavity is changing. Little side fact. It can irk some of the math people out there. Okay, so this is a statement on concavity, which will then let us talk about intervals of a function being concave up and concave down, the same way we talk about intervals of increase and decrease for a function. So I'll do a couple of examples with that. So this is example 2a from page 212, which I bring up because it shows our old friend, the quadratic. Find the concavity of y equals x squared on x between 3 and 10. So my first derivative is 2x. My second derivative is just 2. Now what that tells me is my second derivative is positive everywhere, because we've lost the x dependence on this, so no matter what value x takes on, that second derivative is positive 2. So the second derivative is positive everywhere, therefore y is concave up everywhere. Which should make sense because y equals x squared is just a basic upward facing parabola, so it should be concave up everywhere. Now I'm going to take a look at example 4 on page 213. We're going to want a little space for this. Okay. So example 4, page 213. And in this one we are just given a graph to look at. We're asked to connect that to other graphs. So we're given a graph on a closed interval from -4 to 4. What we're being asked, our y values don't turn out to be too horribly important for this, but our graph looks something like this. 2, 1. something like this is my graph. And this, I am told, is a graph of the derivative of a function. And then I'm asked a number of questions about it. First thing I'm asked is, on what intervals is f increasing? And people do need to be careful about the notation. This is a graph of f prime. So this is a graph of the derivative of f. So when is f increasing? F's increasing when f prime is positive, or when my slope is positive. So when does that happen? That is greater than 0 from -4 to -2, and from -2 to 1. Not including -2, because at -2 my derivative is equal to 0. Or when x is in the set from -4 to -2, join with the set from -2 to 1. So this would be where my function is increasing. My original function is increasing. Not that I have a graph of that to show, but based on what the derivative looks like, this is where my original function would be increasing. B asks, on what intervals is f concave up? I just realized in the first thing I wrote if instead of is. What intervals is f increasing? So on what intervals is f concave up? So f is concave up when my second derivative is positive. But we've got to think about what that means in terms of f prime. So the second derivative would represent the slope of the first derivative. So then my question becomes, I want to make sure that's clearly a double derivative there, second derivative. So when does this thing have a positive slope? It has a positive slope between -2 and 0, and between 3 and 4. C asks, at what x coordinates does f have local extrema? So remember, that's going to happen where our derivative equals 0 or doesn't exist. Now there's no place where it doesn't exist, but it equals 0 at -2 and +1. D asks, where are the x coordinates of the inflection points of f? Circles around these. So f has an inflection point when the second derivative equals 0, but recall that represents the slope of f prime. So where is the slope of this graph equal to 0? It is equal to 0 at -2, and at 0, and at 3. So that's where the inflection point should be at. And E asks us to sketch a possible graph of f. And I'll mention that possible word there in a moment. But what have I just found that I need to talk about? I need to have extreme values at -2 and +1. Need inflection points at 0 and at 3. I need to be increasing up to this first extreme value and between the extreme value and 1, which would imply that I'm decreasing after that. And it's got to be concave up between -2 and 0 and between 3 and 4. And I should have my endpoints in here as well. Okay, so increasing between -4 and 2. Continuing to increase from -2 up to 1, but also changing concavity there. So instead of being concave down, I'm going to switch there to being concave up. But then I've got another inflection point at 0, so I'm going to change from concave up back to concave down. Should make that steeper a bit. Give me something like that. I stay concave down all the way up to 3. At which point I go through one more inflection point for when I get to 4, where I stop. This is one possibility. There are a few things that aren't taken into account yet. I mean, if I just took this whole graph and shifted it up 5 or 6 units, it would have those same properties to match up to here. But let's make sure we've met all our conditions. The function, so this is f. F is increasing between -4 and 2, which it is, and between -2 and 1, which it is. It's concave up from -2 to 0, and from 3 to 4. It has extreme values at -2 and at 1. And has an inflection point at -2, 0, and 3. And I did one thing a little off when I did this. -2 should be an extreme value, but I've just shown it as a flat curve. So really my graph should do a bit more of oh, that's right. Huh, I mixed up in one little spot here. My f prime is staying positive on either side of -2. Since that happens, that means that this is not an extreme value. So, things to be careful of when you check. Alright, I have a couple more examples that I want to go through, although this one is sort of the most involved that way. So, example 7 on page 216. Example 7 on page 216 asks us to find the local extrema of f of x equals x cubed minus 12x minus 5. Now this will look a lot like the first example, but we're going to use the second derivative in this case to figure out what's a maximum or minimum, as opposed to worrying about the signs off of either side of things. So my first derivative is equal to 3x squared minus 12, similar to what we had before. So this equals 0 when x equals plus or minus 2, same as we had before. But now I'm going to take a look at my second derivative. My second derivative would equal 6x. So if I put negative 2 into this, I end up with negative 12. Therefore, f of x is concave down at x equals negative 2. Therefore, x equals negative 2 is at a local maximum. Because if my extreme value has a concave down shape at it, or concave down, so that is going to be the maximum on it. Likewise, if I put positive 2 in, I get positive 12. Therefore, f of x is concave up at x equals 2, and therefore x equals 2 is at a local minimum by the same argument. Okay, our last example kind of pulls a lot of this all together. I'm going to move on to another sheet for this last one. In example 8, on page 216, we are told that the first derivative of a function is 4x cubed minus 12x squared. We are to identify where the extrema occur. Those are going to happen when 4x cubed minus 12x squared equals 0. And if I factor that a little bit, I'll find the solutions of that are when x equals 0 and when x equals 3. Now I'm going to go one step further and look at the second derivative. The second derivative of that will be 12x squared minus 12. And at 0, my second derivative equals negative 12. And at 3, my second derivative equals a large positive number. 12 times 9 minus 12, which is 12 times 8, which is 96. So I have a local maximum at x equals 0 and a local minimum at x equals 3. Part B asks for the intervals of increase and the intervals of decrease. So then I'm going to check some values. For x less than 0, so if I find f prime at negative 1, I get 4 times negative 1 cubed minus 12 times negative 1 squared, which is negative 4 minus 12 is negative 16. Decreasing in that interval. Between 0 and 3, say my first derivative at 1. That's going to be 4 times 1 cubed minus 12 times 1, which is negative 8. Which is also decreasing. That seems, I guess so. Oh, nope. What I just found while I was looking at this tells me that at 0 I shouldn't have an extreme value because it's decreasing on either side of it. What I did was I made a mistake when I worked out my second derivative. My second derivative should be 12x squared minus 24x. Then when x is 0, my second derivative is equal to 0, which implies that is an inflection point, not an extrema. And at 3, I still get 9 times 12 minus 72, which is 36, I think. 36. So it's still a minimum at x equals 3, but there is no maximum at x equals 0. Back down to here, for x values greater than 3, my first derivative at, say, 4 would equal 4 times 4 cubed minus 12 times 4, which is going to be 64 minus 48, which is going to be positive 16, or increasing. So on either side of 3, it's decreasing and then increasing, decreasing and then, wow, I'm doing this backwards, decreasing and then increasing. So that is going to be a minimum value, which is what we found before. So my function is f of x is increasing for values bigger than 3, and f of x is decreasing for values between negative infinity and 0, joined with values from 0 to 3. Part C, we're asked to find where it's concave up and where it's concave down. Kind of have an idea of that already. I know my second derivative is 12x squared minus 24x. This equals 0. I factor 12x out of everything. 0 and 2. So I have inflection points at x equals 0 and 2. So I'm going to do the same checks as I did up here, but with my second derivative and with these as my boundaries for what I'm checking. So for x less than 0, we could say the second derivative at negative 1, and I would get 12 times negative 1 squared minus 24 times negative 1, and I'd have 12 plus 24 is 36, or concave up. Between 0 and 2, so double prime at 1, I get 12 times 1 squared minus 24 times 1, and that's going to be negative 12, or concave down. And then lastly, for x greater than 2, say at 3, so I've already worked it out, that equals 36, so it is concave up. So this thing is concave up for x values up to 0, and for x values bigger than 2, and it's concave down on x values between 0 and 2. Lastly, we're asked to sketch a possible graph of this thing. which has to take all these things into account. So what do I have? I have a minimum at x equals 3. I have inflection points at 0 and at 2. I'm going to wish I drew this out bigger. My graph is decreasing up to 0 and then decreasing again. And then decreasing again. So it's concave up to here. Then it switches to concave down. Then it switches to concave up. And I get a minimum where I need it. That's supposed to be a 3. Okay. That is a big hodgepodge of different things about the first and second derivative and how it connects to graphs. This would be f of x. You will have some questions along with this to try in the Google Classroom, and that's all I have to say about that. Okay, everybody, thanks for listening.